Hello friends, welcome back to my YouTube channel. This is 8th part of my discussion on mass transfer coefficients, and today I will be discussing a numerical example. I'm calling it as numerical number 1, and it is based on the estimation of mass transfer coefficient in laminar flow. So it is based on the discussion that I did in part number 7. I'm giving link to the entire playlist of my video lectures on mass transfer coefficients in the description section. So you will learn how to estimate mass transfer coefficient in laminar flow and then how to use it for finding mass transfer rate. So let us begin the discussion. Okay, to begin with, let us first look at the numerical statement. So water is flowing down a vertical wall 1 meter long in the form of a thin film. The flow rate for the falling film is 0.05 kg per second per meter width at 25 degrees Celsius and 1 atmosphere. The water film is in contact with pure carbon dioxide, CO2. The solubility of CO2 in water at 25 degrees Celsius is 0.0336 kilomole per meter cube of solution. Water is essentially free of CO2 initially. The diffusion coefficient of CO2 in water at the prevailing conditions is 1.96 into 10 to the power minus 9 meter square per second. The density of the solution is 998 kg per meter cube and its viscosity is 8.94 into 10 to the power minus 4 kg per meter per second. So based on this information, we are supposed to estimate the rate of absorption of CO2 in water. So basically it is a problem of falling water film down a vertical wall. The length of the wall is given to us. Length is 1 meter. The flow rate of the falling film is given to us. It is 0.05 kg per second. But it is given per meter width of the film at 25 degrees Celsius and 1 atmosphere. The water film is in contact with pure CO2. The solubility of CO2 in water at 25 degrees Celsius, it is given. It is 0.0336 kilomole per meter cube of solution. Water is essentially free of CO2 initially. So when the contact occurs for the first time, water is not containing any CO2 in it. The diffusion coefficient of CO2 in water at the prevailing conditions, it is given to us. It is 1.96 into 10 to the power minus 9 meters square per second. The density of the solution is given to us. It is 998 kg per meter cube. And its viscosity is also given. Viscosity of the solution is given. It is 8.94 into 10 to the power minus 4 kg per meter per second. So based on this, we have to find out the rate of absorption of CO2 in water. So let us continue with this. Okay, so now first let us look at what is given to us, the given data. So water is flowing down a vertical wall, and it is falling in the form of a thin film. The falling water film is in contact with pure CO2, and during this contact, CO2 is absorbed into water during this contact. So you have a vertical wall, then water is falling down the vertical wall in the form of a thin film, and then it is in contact with pure CO2. So this is vertical wall, water film, and then you have pure CO2. And the direction in which water is falling down, it is y direction, and the direction in which CO2 diffuses through the water film, it is z direction. So mass flow rate of the water film, it is given to us. It is m is equal to 0.05 kg per second per meter width of the film. Length of the vertical wall is given to us. The length, we will denote it by L. So L is 1 meter. Then temperature is given 25 degrees Celsius. That is 25 plus 273.15, which is 298.15 Kelvin. Even though we don't need it in our calculation, we are listing it. Then pressure is also given to us. Pressure is 1 atmosphere, that is 1.013 into 10 to the power 5 Newton per meter square. Pressure is also not required in our calculation. So let us continue with this. Then next is the solubility of CO2 in water. It is given to us. Let us denote it as capital S. So capital S is 0.0336 kilomole per meter cube of solution. And you should know this. Solubility is nothing but the concentration of CO2 in water at the surface. So solubility in this case is nothing but the concentration of CO2 in water at the interface. So that is the concentration at this point, which is on the interface. We denote that concentration by CAI. So CAI, it is indirectly given to us. It is 0.0336 kilomole per meter cube. Then they say that initially water is essentially CO2 free. The meaning is CA0 is 0. The initial concentration of E in the water, it is 0. That is CA0 is 0. Then diffusion coefficient of CO2 in water, it is given to us. We denote that as DAB. So DAB is 1.96 into 10 to the power minus 9 meters square per second. So this is also given to us. Let us continue with this. Further, density of the solution is given to us. That is rho is 998 kg per meter cube. Then viscosity of the solution, it is given to us. That is mu is 8.94 into 10 to the power minus 4 kg per meter per second. And what is the objective? The objective is to find the rate of absorption of CO2 in water. And we will be getting the rate per meter width of the film. So we are supposed to get the rate of absorption of CO2 in water. So let us continue with this. Okay, so let us go for the solution. First, let me tell you what steps are involved in this solution. First, we will be calculating the thickness of the film, that is delta. Then we will be calculating the bulk average velocity, that is uy bar. Then we will be calculating the average mass transfer coefficient, that is KL average. Then we will be calculating the average concentration, that is CAL bar. And finally, we will be calculating the rate of absorption. That is, we will calculate a rate RA average in kilomole per second. And then we will also calculate NA average, which is the mass transfer flux. It is kilomole per meter square per second. So for getting the final answer, we will be following these steps. Thickness of the film, bulk average velocity, average mass transfer coefficient, average concentration, and finally we will get the rate of absorption. So let us continue with this. So first, let us get the thickness of the film, that is delta. And we know delta is calculated by this formula. Delta is equal to 3 mu into m by rho square g raised to 1 by 3. So mu is given to us. It is 8.94 into 10 to the power minus 4 kg per meter per second. Then mass flow rate, that is capital M, is given to us 0.05 kg per second. per meter width of the film. So this is per meter width of the film, you please remember. Per meter width of the film. You please remember it. So let me just per meter width of the film. Then density rho is 998 kg per meter cube. G is 9.81 meter per second square. So you just have to use these values. So delta will be equal to 3 into 8.94 into 10 to the power minus 4 into 0.05 divided by 998 square into 9.81 raised to 1 by 3. And if you solve it, you are going to get delta as 2.39 into 10 to the power minus 4 meter. So in this way, we get the thickness of the film. Thickness of the film is 2.39 into 10 to the power minus 4 meter. Now let us calculate bulk average velocity, that is Uy bar. And Uy bar, it is calculated by using this formula. Uy bar is equal to rho g delta square upon 3 mu. So rho is 998, g is 9.81. So it is 998 into 9.81 into 2.39 into 10 to the power minus 4 delta. We just got it. Square of that divided by 3, and mu is 8.94 into 10 to the power minus 4. So that gives us Uy bar as 0.209 meter per second. So in this way we get the bulk average velocity. Let us continue with this. Okay, then let us get the average mass transfer coefficient, that is KL average. But for that we need to calculate the film Reynolds number, that is Re, because that will decide the equation that we can use for calculating average mass transfer coefficient. So film Reynolds number, that is Re, it is calculated as Re is equal to 4m by mu. So m, you check it, the m as unit of kg per second and mu has unit of kg per meter per second. But you may think that with this it will not be dimensionless, but you please remember the mass flow rate, in this case it is given per meter width, so it is actually kg per second per meter width, so that will make it dimensionless. You please remember this. So m is 0.05 kg per second per meter width of the film. Then mu is 8.94 into 10 to the power minus 4 kg per meter per second. So therefore Re will be equal to 4 into 0.05 divided by 8.94 into 10 to the power minus 4. That gives Re as 223.71, and that is greater than 100. So since Re is greater than 100, KL average will be calculated by using this formula. So I have discussed all this in my previous video. I am giving link to the entire playlist. You please watch it. So KL average, in this case, when Re is greater than 100, it is 6 dAb into m by pi into rho into delta into L raised to 1 by 2. So dAb is given, it is 1.96 into 10 to the power minus 9 meter square per second. Rho is 998 kg per meter cube. Then m is 0.05. Delta, we calculated it. Delta is 2.39 into 10 to the power minus 4 meter. Length of the vertical wall is 1 meter. So therefore KL average will be equal to 6 into 1.96 into 10 to the power minus 9 into 0.05 divided by pi into 998 into 2.39 into 10 to the power minus 4 into 1 raised to 1 by 2. So if you solve this, you are going to get KL average as 2.8 into 10 to the power minus 5 meter per second. So in this way we get KL average. So we have calculated Reynolds number first, and based on the value of Reynolds number we have decided the equation. Since film Reynolds number is greater than 100, we are using this equation. So I have discussed this in detail, which equation is applicable if Re is less than 100, if it is greater than 100, in my previous video. If you have not yet seen that video, you please watch it. Let us continue with this. So next is we have to get the average concentration, that is CAL bar. So we have to get the average concentration CAL bar. So for that CAL bar, it is calculated. What would be the approach? It is calculated by equating the equations for NA average. So we have NA average is given as KL average into CAI minus CA naught minus CAI minus CAL bar divided by ln of CAI minus CA naught divided by CAI minus CAL bar. That is equal to UY bar into delta into CAL bar minus CA naught divided by L. And again, you need to know that we have considered the width of the film is 1. We are doing the calculations per meter width of the film. So that is, you have KL average into CAI minus CA naught minus CAI minus CAL bar divided by ln of CAI minus CA naught divided by CAI minus CAL bar. That is equal to UY bar into delta into CAL bar minus CA naught divided by L. Let us continue with this. So we have KL average is into CAI minus CA naught minus CAI minus CAL bar divided by ln of CAI minus CA naught divided by CAI minus CAL bar. That is equal to UY bar into delta into CAL bar minus CA naught divided by L. So KL average, we calculated it. It is 2.8 into 10 to the power minus 5 meter per second. Then CAI is 0.0336 kilomole per meter cube. It is given to us. CA naught is 0 because initially water is free of any CO2. And then UY bar, we calculated it earlier. It is 0.209 meter per second. Delta, we calculated it earlier. It is 2.39 into 10 to the power minus 4. And L is 1 meter. So we just have to use these values. So it will be 2.8 into 10 to the power minus 5 into 0.0336 minus 0 minus 0.0336 minus CAL bar divided by ln of 0.0336 minus 0 divided by 0.0336 minus CAL bar. That is equal to 0.209 into 2.39 into 10 to the power minus 4 into CAL bar minus 0 divided by 1. Let us continue with this. So we have this equation. 2.8 into 10 to the power minus 4 into 0.0336 minus 0 minus 0.0336 minus CAL bar divided by ln of 0.0336 minus 0 divided by 0.0336 minus CAL bar. That is equal to 0.209 into 2.39 into 10 to the power minus 4 into CAL bar minus 0 divided by 1. That is 2.8 into 10 to the power minus 5 into 0.0336 minus 0.0336 plus CAL bar divided by ln of 0.0336 divided by 0.0336 minus CAL bar. That is equal to 5.01 into 10 to the power minus 5 into CAL bar minus 0 divided by 1. So that is 2.8 into 10 to the power minus 5 into CAL bar, because 0.0336 minus 0.0336 is 0. So we are left with 2.8 into 10 to the power minus 5 into CAL bar divided by ln of 0.0336 divided by 0.0336 minus CAL bar, and that is equal to 5.01 into 10 to the power minus 5 into CAL bar. So in the next step, CAL bar on each side will get cancelled out, and we will have to simplify in that way. So let us continue with this. So we got this equation, 2.8 into 10 to the power minus 5 into CAL bar divided by ln of 0.0336 divided by 0.0336 minus CAL bar. That is equal to 5.01 into 10 to the power minus 5 into CAL bar. That is 2.81 into 10 to the power minus 5 divided by ln of 0.0336 divided by 0.0336 minus CAL bar. That is equal to 5.01 into 10 to the power minus 5. So CAL bar on each side is cancelled. So in the next step, it is 2.8 into 10 to the power minus 5 divided by 5.01 into 10 to the power minus 5. That is equal to ln of 0.0336 divided by 0.0336 minus CAL bar. So I have brought this term to this side and we are getting this. So that is 0.559. So this division is 0.559, that is equal to ln of 0.0336 divided by 0.0336 minus CAL bar. So that is 0.0336. I will take anti-log on both the sides. So that will give me this 0.0336 divided by 0.0336 minus CAL bar. That is equal to e raised to 0.559. So that is 0.0336 divided by 0.0336 minus CAL bar is 1.75. E raised to 0.559 is 1.75. Let us continue with this. So that is 0.0336, 1.75 is brought over here. So 0.0336 divided by 1.75 is equal to 0.0336 minus CAL. Let us continue with this. So we got 0.0336 divided by 1.75, that is equal to 0.0336 minus CAL bar. That is 0.0336 minus CAL bar is equal to, this division is 0.0192, that is CAL bar. It will be 0.0336 minus 0.0192. So that gives us CAL bar as 0.0144 kilomole per meter cube. So in this way we get the average concentration. Average concentration CAL bar is 0.0144 kilomole per meter cube. Now let us get rate of absorption, that is RA average. So the formula for it, RA average, it is calculated by using this formula. RA average is equal to U bar Y into delta into CAL bar minus CA naught and into 1, delta into 1 into 1. Why 1? Because we have unit width. So that gives us our UY bar is 0.209 meter per second. Delta is 2.39 into 10 to the power minus 4 meter. So CA naught is 0. Therefore, RA average will be 0.209 into 2.39 into 10 to the power minus 4 into 0.0144 minus 0. So all values I have used. So that gives me RA average as 7.21 into 10 to the power minus 7 kilomole per second per meter width. So in this way we get the rate of absorption, that is RA average in kilomole per second. Then let us get rate of absorption, NA average, kilomole per meter square per second. So NA average, you can calculate it in this way. NA average is equal to KL average into CAI minus CA naught minus CAI minus CAL bar divided by ln of CAI minus CA naught divided by CAI minus CAL bar. Let us continue with this. So rate of absorption, NA average. So NA average is calculated as, you have the formula, NA average is equal to KL average into CAI minus CA naught minus CAI minus CAL bar divided by ln of CAI minus CA naught divided by CAI minus CAL bar. So KL average, we calculated it earlier, it is 2.8 into 10 to the power minus 5 meter per second. CAI is 0.0336 kilomole per meter cube. CA naught is 0. CAL bar, we calculated it just now. So CAL bar is 0.0144 kilomole per meter cube. So therefore NA average will be equal to 2.8 into 10 to the power minus 5 into 0.0336 minus 0 minus 0.0336 minus 0.0144. We are using the values, divided by ln of 0.0336 minus 0 divided by 0.0336 minus 0.0144. So we have NA average is equal to the previous equation, 2.8 into 10 to the power minus 5 into 0.0336 minus 0 minus 0.0336 minus 0.0144 divided by ln of 0.0336 minus 0 divided by 0.0336 minus 0.0144. So that is Na average is equal to 2.8 into 10 to the power minus 5. So if you simplify it, it will be 0.0336 minus 0.0336 plus 0.0144 divided by ln of 0.0336 divided by 0.0192. So that is Na average is 2.8 into 10 to the power minus 5 into 0.0144 divided by 0.6. This is 0.6. So Na average, it comes out to be 7.2 into 10 to the power minus 7 kilomole per meter square per second. So this is how we get Na average. You can also calculate Na average by using this formula. Na average is Ui bar into delta into Cal bar minus Ca naught divided by L. Ui bar is 0.209 meter per second. Delta is 2.39 into 10 to the power minus 4 meter. Cal bar, we calculated it earlier. It is 0.0144 kilomole per meter cube. And Ca naught is 0. IL is 1 meter. So if you use these values, that will give Na average as 0.209 into 2.39 into 10 to the power minus 4 into 0.0144 minus 0. So I am using the values divided by L is 1. So Na average comes out to be 7.21 kilomole per meter square per second per meter width of the film. So Na average is 0.21 kilomole per meter square per second. So you must have noticed Na average calculated in both the ways, it is almost the same. And since the length is 1 meter and you are calculating it per meter width of the film, even Ra average has the same value. You must have noticed. So in this way, we finally get the rate of absorption. So we have learned how to calculate the mass transfer coefficient and then how to use it to find the rate of absorption. So I hope you must have understood the steps that I have followed. If you have any doubts, you please mention them in the comment section. For now, I am going to end my discussion for this video lecture. From my next video lecture, I will be starting my discussion on mass transfer coefficients in turbulent flow. So for now, thanks for watching the video lecture. Thanks for watching the video lecture. Do subscribe to my channel. Tell your friends to subscribe to it. Hit the bell icon so that you will be notified as soon as I upload any new video on my YouTube channel. For now, have a nice day and hope to see you soon in my next video lecture. Thank you. Have a nice day. Bye bye.